At chapter 5 at the end, we're talking about average value function. That's the last section, 5.5. And so if we have some type of function, y equals f of x, so here it looks like this. And we know that on this graph we have y values, right? There's a couple negatives down here, here's positive, here's 0. So if I take all these y values and I add them up and then divide by how many I take, that would give me an average, right? Well, this can keep on going forever, or I could do more and more values, right? More and more y values. So if I'm going from, say, A to B, and I want to find what is the average y value from A to B, that would mean I'd take up all the y values, so I'd start adding them up, right? Here's my first y value, here's my second y value, and I would just keep on taking these y values and just adding them up until I get to however many y values I want, right? F of x to the n. And so I'd add all these up, and then I would divide by how many I have, right? Divide by n. Well, it depends on how many n's I want, right? So if I want an infinite amount, then what I would do is I would want to find, I want my x's to not be random, right? So I want these x's to be the same distance apart from each other, right? So that's when I take from A to B, find that distance from A to B, and divide by how many numbers I want, right? And that will tell me what my change in x would be. Because I want to find these y values at the same distance, right? I don't want to find one at 1 and the next one at 3 and the next one at 3.5 and plug in those x's to find my y values. I want to plug in 1 and then 2 and then 3 and then 4, right? And then 4 and then 5. I want those x's to be the same distance apart so they can kind of be uniform. So that will tell me what my distance in between my x's are. And then I would plug those x's in to get my y values, and then I would add them all up here. So I'd add them all up and divide by that number n, how many I have, right? Well, n, if I just manipulate this a little bit, I can go ahead and switch these places. So a minus b over the change in x would equal n, the number of times that I'm adding these up, right? So then if I take this, a minus b over the change in x, I can when I multiply by a fraction, I am dividing by the reciprocal. So I can go ahead and switch this around to f of x1 plus f of x2, and so on all the way to f of xn. And then divide by a over b, a minus b, sorry, and then times that by the change in x, right? So I'd be multiplying that. Well, as I look at this further, I could rewrite this as, say, 1 over a minus b times f of x1 plus f of x2, and so on all the way to f of xn, and times that by the change in x. So as we increase this, as this gets closer and closer, as my change in x gets closer and closer and closer to 0, those difference of the x's get smaller and smaller and smaller, right? I'm doing more and more points. So I'm doing more and more points on this graph. These points are getting closer and closer and closer together, right? So I'm getting more and more and more and more and more, increasing that without bound. So as this turns into more and more and more and more, then this goes to infinity, right? The number of times that I'm adding it, this number would go to infinity, the number of y values that I'm adding. So that's looking at the sum of I to n of all the way, or from I to 1, 1 to n, of all my f of x's. That's where this little asterisk kind of thing comes like that. And that's being times by the change of x. And then I'm multiplying that by 1 over a minus b. And we remember this part as the integral. So that is the definite integral, right? From a to b of f of x, and change of x gets to switch to dx, and it's times by, this is what we call the average value of a function. So this is our average value of function, f fave. So that's the average value of a function. So that will tell us what this average value is. And it's somewhere in between there. So there's some value c in between there. So that's the average value of function. This would be our fave, our average value function. So we can find that average value function of taking the integral of our function and then timesing it by 1 over a minus b. So I have to have an a and a b where I'm going, and there's some y value that all our x's will be, or one x value will give us this y value here. So this is a y value. So we add up all our y's, and it's going to be some y in the middle. So there exists some x that will actually give us this y value, and that's what we'll get to later as the mean value theorem. But as for now, we can find the average value of a function by taking the integral of that function and timesing it by 1 over a minus b, and that will give us the average value of a function, which is a y value. All right, so here's a quick example. Find the average value. So the average value of a function is 1 over a minus b times by the integral from a to b of f of x. So here's our f of x. So I'm taking the integral of that from a to b. Our a is -1, our b is 2, and then I times that by a minus b. So -1 minus 2, or b minus a. It is actually b minus a. b minus a. So that is 2 minus 1, or minus a minus 1, sorry, which is a plus 1. So 1/3 times the integral. So x plus 1/3 x cubed from -1 to 2. So I'm taking the integral of that, or integral of 1 plus x squared, which is x plus 1/3 x cubed. And then I can go ahead and plug in my 2. Subtract, plugging in my -1. And then times that by 1/3. So I evaluate that, and I get 2. So my average value function is 2. So this graph looks something like this. All right, it looks something like that. So the average value that runs through here is 2. So there's 1, 2. So this is my average value right there, is 2. All right, so what I alluded to earlier is the mean value theorem. I said there is some x value that is actually going to give us that average value function. So that's what the mean value theorem says. It said even though we have this graph, looks like this. Here's our average value function. What the mean value theorem says is there's some x in between a and b. So there's some x value, we'll call it c, between a and b that is actually going to give us a y value of that average value function. So for example, on this graph where I drew, my actual c would probably be right here where it intersects, right there. So what the mean value theorem says is we can solve for our fave, and then what we can do is we can set that equal to our function. So whatever our function is, f of x, we'll set it equal to our fave average value function, and then solve for x and just label that xc. And so that's what it says. So you can rework that. Here's what the mean value theorem is. We have that equals our fave. Now we just set it to f of c. And so we set that value to equal to f of c. So that means we're just plugging c in for x and then just solving for c. And you can rewrite it like this. So our integral is equal to f of c times b minus a. So we can go ahead and practice on this one. Okay, so we have the same thing from before. We said our fav equals 2. So what I'm going to do is I'm going to set f of c equal to 2. And so that means I'm just plugging in c in for my x. So instead of x squared, it's now going to be c squared equals 2. And then I'm just going to solve this. So c squared equals 1. So that means c equals plus or minus 1. And I can get, yep, so there it is. It equals actually 2 values from a to b. So my a equals -1 and my b equals 2. And so these two numbers, 2 and -1, go into both of those, right? It fits within those. So these are our two values that give us, that make our, when we plug them in, they equal our average value function. All right, so here's another way to relate average velocity and our average value function. So we want to show that our average velocity of a car over a time, from start of the time to the end of a time, t1 and t2, is the same as the average of its velocities during the trip. So the average velocities during the trip would be our total displacement over our total time, right? Or our change in displacement over our change in time. So if we let s of t equal our displacement, then we have s of t 2, displacement at time 2, minus the displacement at time 1, divided by our change in time, which is time 2 minus time 1. That would be our average velocity over this time interval. Okay, now if we take and we find out what our average of the velocities. So average of the velocities means that I have some velocities throughout our trip here, right? So I have, say these are my velocities, right? So this is velocity, and then the average velocity would be our fav, right? So that would be taking our a and our b, subtracting them, so b minus a. So b minus a would be this, 1 over that times the integral from a to b of our function, our velocities function. Okay, well, the antiderivative of our velocities function is our position function, right? S of t. Okay, then we take the different integral, but we got to take this from a to b, which is t1 to t2. So plugging that in, that is s of t2 minus s of t1, all over, times by that is just this, and that equaled our average velocity. So this is our fav, the average of our velocities, and this one right here is our average velocity. So this is our average velocity of a car over their time interval, and this down here is our average of our velocities, which is the same. So these are the same. So that's how we kind of relate and how we use our average velocity and average of a function, average value of a function.